it will be a talk more related to cosmology. My idea it was like it is to try to introduce some approach that we use in cosmology that maybe in the future will have also could be also used maybe to things more related to gravitational wave and to gravitational wave searching with the LIGO and then the LISA when they will be the case. So what I will do, I will introduce this new formalism based on new coordinate system that we have introduced some years ago, just as like coordinate, and I will give it some application. So the outline of the talk is the following one. First, I will give some motivation that push people to go beyond Newtonian gravity and beyond linear order perturbation theory, study cosmological large-scale structure observable. And I will introduce the geodesic like coordinate and the relation to cosmological observable. Then I will see how to use this coordinate to write up to second order in perturbation theory in the Poisson gauge, a cosmological observable like the luminosity distance, the area distance, or the number count. And then I will give another example, maybe more related to gravitational wave, or could be a gravitational wave used to find the, let's say, a use of this result. That is the evaluation of the time of flight difference between ultra-radistical particle with different mass or energy emitted by a distant source that could be a supernova or could be a gravitational wave event like a sparring between two black hole or black hole and neutron stars. This you know much better of me. And then I will conclude. And the talk is based on a series of papers in collaboration with Ido Vendayen, Enea Dio, Ruth Durer, Giuseppe Fanissa, Maurizio Gasperini, Francesco Montanari, Fabiano Uger and Gabriele Veneziano. So, let me first introduce the general problem. We have nowadays cosmology has entered the precision era with the first main source of data, which is given by CMB anisotropy, which is a two-dimensional data set, and for which the link between data and the data theory is made using mostly linear perturbation theory, and the large part of the information is encoded in the power spectrum, as shown by Planck collaboration. In particular, you can see the power spectrum here for temperature anisotropies. On the other hand, we have that the second main source of data is given by large-scale structure present and future large-scale structure survey, for which which is a three-dimensional data set, on which we measure two spatial and one light dimension. We look on our past light cone. For this large-scale structure, we have that on intermediate, different from the CMB, we have for large-scale structure on intermediate to small scale, the nonlinearity can become important, so we have much more information because we see really how the matter interact and form structure, but the analysis is much more complicated. And the key point is that to extract information, to do new physics, we don't only need to have an accurate observation, but to have also an accurate description of the large-scale structure that go beyond beyond what is known now, beyond linear order. Sure. Okay, for the moment, what is taken is in practice the count number of galaxies for redshift bin, and redshift bin is a small angle. And what is done now is the two-point correlation function. And in the future, what they want to do is to evaluate a three-point correlation function, for which is particularly important in the clustering of galaxies and go beyond linear order. This because let's say, the three-point correlation function is the best way to relate the large-scale structure to, let's say, a primordial universe, like to evaluate, for example, FNL and the primordial non-Gaussianity. This can be. I will more show how to go beyond linear order with this approach, because I thought more to give the formalism that it can maybe apply to other field. That to go and describe the truth. Let's say for the moment there are not enough data points. But for example, with this, that today during the weekend and today there will be on the archive the data. They are beginning to think about this. And for example, I spoke with Rogerio 2 weeks ago, and he said me that they will try to look to the correlation, to the three-point correlation function starting from next year, starting from the second release of this. For the moment, let's say that they look to the Newtonian and counterpart of the three-point correlation function. When the Newtonian part, there is no information about the early universe. The point is that you have to clean the information from the Newtonian contribution to get really the relativistic contribution, the one that is given by the fact that we look on the light cone and so on, and to arrive from that to the primordial one, to the final primordial. But this is something that is quite complicated. There are a lot of different physics go in, so they are still doing. Yes, this is long. Oh, you mean how much time ago is this one? There is SDS, there is Euclid, there are a lot. I mean, I may 10 survey in the next 10 years, probably. No, there is also the radio, that is will be SCA, that will be, so it will not count galaxy in this case. It will see the intensity of the emission, of the hydrogen emission. So it will be like, can give more far, it will be less precise, so you cannot distinguish between two galaxies near, but it will go more far. So going more far, the nonlinearity are less important, and the relativistic effect, like for example, lensing contribution is more important. So you lose from precision that you cannot count galaxies, but you earn because you are going to look more far in the past, let's say. So mainly we saw optical and the radio, mainly, let's say, for what I know, of course. Nothing. So what we have to really ask ourselves to go in the direction that Ricardo was pointing out now is what the last structure, what we are really observing when we look to this survey. The fact that is that the observation were made on our past light cone with redshift in common photon direction as an observational coordinate. So for example, when we see our density fluctuation, we see density fluctuation farther away, farther in the past. So they are more linear, more we are going farther in the past. And then we have that the measure redshift is perturbed by the peculiar velocity of the galaxy, how the galaxy move around, and by the gravitational potential. The same volume is distorted. The angle that we are looking, they are not the angle to which the source is to the position of the source, because our photon, they deviate as a consequence of lensing effect. Like, for example, when I look to strong lensing, when a photon pass near a star, this is deviated by the star, and this is in practice the same, but here the photon from really far away source, they are deviated by, let's say, stochastic distribution of inhomogeneities or large scale structural inhomogeneities. So this is called, for example, weak lensing. So we have that for small redshift, for small galaxy category, for example, up to redshift 1. This can be, when we go up to redshift 1, this can be relevant. They are already relevant, for example, for SDS, BOSS, and so on. But of course, this will be much more important in the future, where we will, for example, for DES, the new release, as I said, we try to look to 3-point correlation function for big BOSS, and of course, much more for Euclid, where we will have data in 7-8 years, probably. Yeah, maybe less. So, summarizing, we have both our observable coordinate and the observed volume are distorted by the percent of inhomogeneities, and the two main, let's say, physical effects that contribute to the physics of the 2-point and 3-point correlation function are the standard Newtonian effect, so density, redshift, space distortion, and the relativistic effect, the one that are there because of general relativity. So, for example, lensing, the deviation of light, gravitational potential, and so on. To take all these effects in consideration, for 2-point correlation function, we have to go beyond Newtonian gravity, while for 3-point correlation function, where the measured part of the information are, for example, we can use it to look to the primordial non-Gaussianity, we have to go both beyond Newtonian gravity, but we have to go also beyond linear theory. Redshift space distortion is given from the fact that, for example, you look to a volume, and this volume, because all the galaxy that you want to measure inside this volume, they are moving around, so you have a distortion of the volume that you are watching. So in practice, is the derivative of the velocity with respect to the radial direction. So this velocity, this galaxy, they have a velocity. This velocity, we have a component on your radial direction, and they will change if you look to a volume, for example, like this. This velocity, you have a different galaxy. and these have different velocity. So, and for example, like this. So this velocity will also change in your radial dilation. So when you are looking to this volume, you don't really look to this volume, but you look like to something like this, or something like this. So there is a distortion of the volume that you are looking, because this direction, this. Yes, because when you look to the redshift, you don't have this derivative. The redshift will depend just from the parallel velocity, radial velocity. When you look, for example, to this effect is present, for example, in the number count, when you count galaxy, and it is go like this. So like the radial velocity, the radial derivative of your velocity. Yeah, sure. You go like this. Sure. It is H, yes. Sorry. My indented writing is a mess. No, actually is the bigger one, together with density. Together with the density contribution, the fluctuation of the density is the larger effect that you have. It's considered the Newtonian effect. So it's the one that you have to, let's say, if you want to look to your signal and use your signal to go back to primordial universe, then you have to clean up with this effect. And because this and the one from density, that they come like this, they are the larger, so let's say like this. They are the larger effect that you have. So what it is, let's say, nice, that we point out, we were not the only one, is that this effect, they are autocorrelated. So if you take two different redshift, you look to the 2-point correlation function on two different redshift, then this one, they go down because there is no autocorrelation by effect, the relativistic effect, like for example the lensing, they don't care about this and they stay constant. So you have some hope to see them, but you have to have a survey that go deep in redshift, so you can take different point at different redshift on this survey. You have to be clear. You have to not have a large noise. Sure. Sure. No. Mm. Yes. I mean, yeah. Let's say that I mean, the way to separate this effect is looking to different time. Like you take a 2-point correlation function, you don't look to the same redshift. You look to two different redshift. Mm. Yes. So yeah. Okay. So I understand. Okay. For the one that you have different velocity. There is a one component that comes from perturbation theory that comes really from the evolution of the universe, that we have a similar time scale like the density, because it is a fact that in practice is the same, is the density, I mean the gravitational potential is a source of both effect, and so they come from the same source. Then there are other velocity that, for example, the velocity of the of your star inside the galaxy and so on. That one, they have a different time scales. As you point out, you can, let's say, distinguish, you can clean up using this. Yeah, sure, that's true. But it's also much more difficult to measure them. But if you can measure them, then you can use the fact that they're on different time scale to clean up the signal. No, nothing. I didn't think about it. That's a good point. So let me now, in practice, so the point that to go beyond, so in the past we tried to see how it was possible to measure this three-point correlation function. And to measure this three-point correlation function, one they have to go beyond the linear theory, because if you have just linear theory, you consider 3-point, then the 3-point correlation function will be 0 for weak theorem in practice, because your fluctuations are stochastic, so you have to go beyond the linear theory. But the point is that to define, to describe this observable beyond linear order is really complicated. I mean, they get really involved. So a way to do this is to use a gauge, a system of coordinate we introduced in the past, and we call the geodesic icon coordinate, where the description of such cosmological observable gets much simpler. So this system of coordinate is given by this metric, and they have 6 arbitrary and they have 6 degrees of freedom. So it's in part gauge fixed, but not totally. And these 6 degree of freedom are given by a function upsilon, a two-dimensional vector A, a symmetry on tensor gamma and B. Then, looking into this metric, one can see the following property. We have the W is a null coordinate, namely the mu W is equal to 0. The mu tau define a geodesic flows, namely is the vector that describe how your free-falling observer move, for example, a galaxy. And k mu, which is the derivative of W, is the photon momentum. We describe the null geodesics from your source to your observer and show how photon travel at constant W and constant angle, theta tilde. So, just to give the geometrical interpretation. Yes, yeah. So here they are. So if you want to look to, I mean, it's hard to understand just looking to the metric. So let's look to the geometry. So if you do the spatial flat Freeman-Robertson work limit of the coordinate C before, we have that W is just the radial direct distance plus the conformal time. So is your past icon at background level. Tau is the proper time. Upsilon is the scale factor. UA is equal to 0 because you have no anisotropy. And then you have that gamma A B, the theta I, the theta B is just a two-dimensional metric on the sphere. So if we generalize to homogeneous space-times, you can easily understand from what we saw before, from the homogeneous limit, that W, you label your past light cone. So W equal to constant is the non-perturbative description of your past light cone. Then we have the tau, being the mu tau, the vector of the free-falling observer. Then you have the tau is the time in the synchronous gauge. So it's the time of your free-falling observer. So if you have a free-falling observer with a clock, this will measure tau. Theta tilde A are the direction of the observation because the photon travel at constant theta tilde A. Then we have the upsilon is the degeneralization of your scale factor, let's say inhomogeneous scale factor. A gamma AB is the metric on the two sphere at tau constant, at time constant, embedded your past light cone. So it's the sphere where all the source that you have the same time, they lie on. And the UA is just a measure of your anisotropy. It's like a lapse function, let's say. You measure your anisotropies. Upsilon. I believe. Is X dependent. So at background level, it depends only from the time. Then if you go beyond the background level, then it will depend on all these functions. Will depend on W, will depend on tau, it will depend on theta. So let's say if you go back to Freeman-Robertson work and you do like a coordinate transformation, like I will do now, then it will depend from space, time, and all. I don't know them. I think yes, because this one is really your the generalization of your scale factor. I mean, the redshift is at a non-perturbative level, just given by upsilon, just given by the radio between two upsilon. So what you have is that if you look to the redshift, to the non-perturbative redshift, then it's just defined by k mu, u mu. K mu is the photon, u mu is define your observer. So if you take the free-falling observer, you write down, then you have that your non-perturbative redshift is just given by upsilon at observer position over upsilon at the source. So it's really the non-perturbative generalization of your scale factor. Here, when I use some subscript like OS, I mean at observer at source, of course. Then you have that in this gauge. If you look now, if we look, for example, to one of the observable that is used in large scale structure, or in general in cosmology or astrophysics, namely the area distance, we can define the area. First of all, if we consider the territory or reciprocity relation, this is related to the luminosity distance. Sometimes is used, but this is following the relation that is valid if you don't have cuspid. If you have cuspid, then this relation is not valid anymore. And the area distance is just given by the cross-sectional areal element perpendicular to your left right at the source over the infinitesimal solid angle at observer. Namely, you have your angle, you see your source at some areal element, you do the radio, you have the distance between the two. So then what you can see using the GLC gauge is that you can have an exact expression for this area distance. You cannot have just an exact expression for the shift, but you can write in exact way the area distance. You do this using the so-called Jacobi map. The Jacobi map is the matrix which related the shape of your light beam to this initial value. I mean, you have your light beam, and then this light beam go through inhomogeneities, and is modified by these inhomogeneities. And the way in which is modified, projecting on the screen space, so the space that is perpendicular to your light beam, is described by this matrix that is called the Jacobi map. What we have, that if I look to the geodesic deviation, where lambda here is the affine parameter that describe how he described in practice, parameterize your light beam, and I consider the projection of xi mu, I mean the vector, the vector that define the deviation between two near light beam, two near photon in practice. Project this along the Sachs basis. I mean, along the Sachs basis is the basis that describes your screen space. So there are two parallel transporter for vector, which give the orthonormal basis of the perpendicular space to your light beam. Then I define this way. Then I can show that the Jacobi map, okay, this is just formalism. The Jacobi map can be defined in this way. Is such as that we satisfy this equation, and with this initial condition. Then what one can do using the Jacobi map, using the GLC gauge and putting all these equations in GLC formalism, is that the exact solution for the Jacobi map is just given by this. And then we can use the fact that the Jacobi map is connected to the area distance by the following relation. Namely, we have the area distance square is just the determinant of the Jacobi map. And then from this, we can see that the area distance square in GLC formalism is just given by the square root of the determinant of the matrix gamma b, which in fact describe this sphere. So in practice, you have this sphere, you have this gamma b that describe the two sphere. And then you have your photon that they travel on this two sphere. So then if you do the square root of the determinant, you have the area distance. So in some way you could guess before to the question, let's say. However, over some contribution that will depend only on the observer position, that is usually not considered in cosmology and in general in astrophysics, because it will be related to the monopole, to the pole of your observer that are not well known. In any case, you cannot describe in perturbation theory. So then let's look. Now let's look to another. Let's see how this can use also to describe other cosmological observable, like for example the galaxy number count. The galaxy number count, as I was saying before, is the number n of galaxy, source, let's say galaxy, for solid angle and the redshift. Then the fluctuation of this galaxy number count is defined in the same way. So the number of your observable galaxy, for example, less the average over the average, where n it can be done by the density of your source times the volume at fixed direction of observation and the redshift. Then if you do perturbation theory, you can expand this quantity in the following way and write the perturbation on the number count like this. This will be an observable quantity. You mean will give the number of galaxy per unit volume and unit redshift, and so is a gauge invariant quantity. I mean, with gauge invariant quantity, I mean that you can use whatever coordinate system that you want to evaluate it, and you will have always the same solution once you write it in function of what you observe, I mean, redshift and direction of observation. Then if we look, for example, through the three-dimensional volume element, I mean, to this part, then this in general, as seen by your free-falling observer, or in general by an observer u mu, it can be written in this way. And then if we go a coordinate transformation, if we go to observable quantity, you just insert the Jacobian, and you can write this way. Then one can easily see if you take this, and you consider your variable x mu like the GLC variable, then this is simplified, and you get just this result. Namely, you have that the volume perturbation is just given by the square root of your determinant of the method of your metric, two-dimensional metric, namely the area distance square, times how your proper time change with the redshift. I mean, you have an observer, and your free-falling observer measure time. How this time change with the redshift, it will give the part that is missing to go from the area distance to the volume perturbation. In particular, this contribution you have inside the redshift space distortion. And this expression is a non-perturbative expression. I mean, it's valid to already in perturbation theory, also for the non-perturbative metric. And then, if as a consequence, you could know also the density in a non-perturbative way, things that we don't know because, I mean, for clustering and so on, then we could write a number count non-perturbatively. So now, yeah, sure. Is exact. I mean, if you don't assume graphing, you don't assume how to describe your inhomogeneities, then if your photon they don't travel through cuspid, because otherwise, of course, it's not well defined the direction of the photon. Then, if you don't have this, then the volume the perturbation of the volume, as you seen from the observer, it can be right just like this. This is non-perturbative expression. Then, if you go to perturbation theory, for example, we know how to describe the large-scale structure, for example, only in the Poisson gauge or in the synchronous gauge where you do perturbation theory. Then, if you want to express this quantity in that gauge, you have to do a coordinate transformation. That I will do now. So let's do this coordinate transformation. I mean, now you have an exact non-perturbative description of your large-scale structure on all scale, let's say. But we don't know how the inhomogeneities are described to all scale. We know only through any-body simulation. And we don't have a solution of fast an equation GLC gauge. This is, let's say, something I'm working on now, but we don't have it at the moment. So to really see what is the effect of these inhomogeneities on this photon, on the travel of the photon, on the large structure astrophysics observable, you have to go to a model, we have to consider a model which describes your inhomogeneities. And if this model is given in a gauge, in a coordinate system which is different from GLC, you have to connect GLC to this coordinate system. You have to do a coordinate transformation. For example, let us consider a stochastic background of scalar perturbation, like, for example, the one that comes from inflation, and which, for example, in the Poisson gauge. In the Poisson gauge, we have the tensor metric. If we assume a matter source with a vanishing anisotropic stress, for example, how it is if we describe our universe with lambda CDM, then we have that linear up to second order linear perturbation theory. This tensor metric can be described in the following way. I write it in the radial coordinate because it's more easy for the coordinate transformation. And now to express our non-perturbative result in this metric, we have to connect GLC to this Poisson gauge. This battery. No, because when you go, I mean, in general you can, but in this particular case, no, because here you assume to have just 1 degree of freedom. But so you assume, okay, understand? Yeah. But then these are connected by a question of motion, because when you go, yes, but it's to second order they also connect with tensor and vector. So then it's more complicated to second order. So you cannot describe, for example, to second order just by this. So you are just linear theory, you can. But then when you have shell crossing and so on, then you need the vector and tensor. So then I think you cannot just use this. Yeah, but then you will have yeah, but then in general your perturbation, for example, on the radial part of your metric, it will be more complicated. It will not be just this. This, for example, is a diagonal matrix, diagonal element. But then if you really want to describe the universe, you have also off-diagonal contribution. So you have stuff that move around, I mean. So you cannot just use the diagonal part. But if you stick to large-scale structure, and let's say mid-line or linear regime, then this metric is fine. Let's say up to, I don't know, maybe one megaparsec square, let's say, 0.1, maybe. So then you have to connect to use this. You have to connect GLC form to this metric, and you can do this like coordinate transformation, like Jacobian, where we do the following hypothesis: non-singular transformation around the observer position. We consider we are not in a black hole, let's say, and then the two-dimensional spatial section at equal constant is locally parameterized by the observer position by standard spherical coordinate. Namely, our theta tilde A can be just a standard spherical coordinate, so they are just our direction of observation. Then, okay, this is just, I put just to show how much is complicated. So in practice, yeah, okay. So let me first introduce two auxiliary quantity that are P and Q. P, the radial derivative of P is just the radial velocity, and Q is just the integral Sarsgaard effect. So, I mean, this one, it defines the perturbation of the redshift. And then eta plus minus is just a background, is just a useful, like on the background variable. Then, if you do your coordinate transformation, you go to second order, you get this really complicated expression, but it's just algebra, it's nothing of too bad. And then, using this and going back to your metric, you get these two, you got the following entries of your metrics. The generalization of your scale factor, the term that in practice define like how they produce anisotropic in your spacetime, and this one they will say how your two-dimensional term is, how your Pascal sphere is perturbed and how it changes and so on. I mean, it define your Jacobi map in practice. But let's just don't care about the full and complicated expression and see how we can use them. So, first of all, let's see. First of all, we have that this expression, the one that they define the generalization of the scale factor, using the expression for the shift saw before. It can be used to define your redshift at first and second perturbative order. So at first order, you get the following quantity, where I neglect the term that comes from peculiar velocity, gravitational potential at the observer position, because these are in any case are not observable. So as Riccardo was saying before, the redshift at first order, you have inside a perturbation that it depends from the radial, from your peculiar velocity of your galaxy, for example, from the gravitational potential, and from a term that is connected to the integral Sarsgaard, that in any case is much smaller of these other two. Then, to second order things, you get more complicated, and you get the following expression, where with this one is, as I said, now it is the radial velocity, while, for example, V is just the potential that is associated to your velocity. So, for example, the derivative respect the angle is your transverse velocity. So how the radial velocity is like how your galaxy move or your radial direction, transverse velocity, how they move perpendicular to your radial direction. It is transverse velocity going in only when we go to higher order in perturbation theory. It doesn't appear to first order in perturbation theory. This kind of expression can be found in the following pattern, so by myself, our group, and by other group, in particular by the one that works in South Africa. So then, now we have the redshift perturbed up to second order, we have our direction observation, and so on. So now we have to ask ourselves how we can write our cosmological observable in function of this observational coordinate. To do this, we have to follow the following three steps. So the first step is to expand the expression for area distance and number count in function of Poisson gauge coordinate using the coordinate transformation. After that, we have to, but what we really observe is the redshift. So as a second step, we have to expand conformal time radial coordinate in Poisson gauge in function. We have to construct a fiducial model that is described as a perturbator redshift, namely solving these two equations where the left hand side, solving the left hand side with respect to the background, it gives you the background fiducial model that is associated to the observed redshift. Namely, this is the observed redshift. We construct a fiducial background value of your conformal time that describes the observed redshift, and then we expand our coordinate on this fiducial background. And this way we can construct a new perturbation theory where now is around your observed redshift. And as a third step, we have to express what we have in function of this fiducial model, in function of the direction of observation, using the fact that we can invert the coordinate transformation we saw before, and we can write the angle at the source in Poisson gauge in function of the one at the observer, the one that you observe, plus some contribution from perturbation theory. And we have to just go to first order because at background level, nothing depends from your direction of observation because you assume isotropy at background level. If, for example, you go in a, let's say, Bianchi 1, then this is not more anymore the case. You have to go to second order also for the angle. So step 1 is just algebra. You have to take your observable, use your coordinate transformation, pass 1 week, and you get your result. So, for example, if we, namely we will start from our result expression for area distance and from number count, and from a perturbative expression to second order for the density, because the density is not in exact way, and then you use the expression for the volume perturbation that we did before. You put in your machinery and you get your expression. Then to step 2, instead we have to found our background physical model. So this we have to expand conformal time, radial Poisson gauge coordinate around the background model, and the results are just given by this. When I write this quantity, for example, when I write 1/2, it means that I Taylor expand first order perturbation theory around the background model, and then this will give this contribution, and then you can construct your background physical model. For example, it's nice to see that, for example, for the when I look to the redshift, I write what is the contribution to second order given by the perturbation of the redshift to first order. Then you get a term that they go like redshift space distortion. But this term, it doesn't. But then when you look, for example, to the other distance, this kind of term they raise each other and they don't appear in a final expression. So this is something that is non-trivial. Also is a non-trivial check of the result. Then, as a final step, if, for example, we assume to have a general, let's say, variable written from first step, so let's say general variable that we have perturbation theory in function of Poisson gauge coordinate, we take this variable, we Taylor expand around our background physical model, and we obtain such a variable, write in function of the observer redshift, that will be your background physical model. Now, in practice, your conformal time, your background conformal time describe the observer redshift, but still in function of the angle in the Poisson gauge. But we want to write this in function of the angle at observe, the one that you observe, the observer position. So you have again Taylor expand again, and we in this way, and we will get your variable that we call it with an at just to avoid confusion. You will get in function of observed redshift and direction of observation. So just to show you the result to first order, we have that the second order homogeneous and non-average expression for the luminosity distance, for the area distance, it is the typos, is given in a conscious form in this way, and to first order perturbation theory by the following quantity, which is an expression is valid for any dark energy model with vanishing anisotropic stress tensor. It was generalized to consider the anisotropic stress tensor in this publication. And here you can find all the second order expression obtained inside the GLC form, inside the GLC approach. Of course, this disagree with the one in the lecture by Bonvin, Durer, and Gasparini in 2006. Similarly, for the number count, we can write the number count to first order in perturbation theory using the GLC in the following way. And the second order expression, considering also anisotropic stress, you can find this in this paper. And in this paper, you can also find also the physical, let's say, meaning of all this contribution. For example, I don't know, this one is what is called the Shapiro time delay. This one is the convergence or lensing contribution, and so on. This one is the redshift space distortion, density, and so on. So let me make the conclusion of this first part of the talk. So we have presented the GLC coordinate, which is a coordinate system that is adapted to an observer in spatial icon. Using this coordinate system, we can describe the last structure observable in a exact non-perturbative way. And we have shown the standard procedure to go from this exact expression to expression in perturbation theory. And then we can apply this kind of result in a lot of different ways. For example, we can see the back reaction that these large-scale structural inhomogeneities have on the area distance redshift relation, which was done in this paper, and also to evaluate what is the theoretical description of the dispersion of data. Namely, you have a lot of data, how they will be scattered with respect to your homogeneous value, that which will be the variance that is associated to first order perturbation theory, which was also done in this paper. And then we can evaluate the number count B-spectrum, I mean, a 3-point correlation function, that this is what we hope to measure in the future, that it was evaluated for the first time in L space and redshift space, using all the relativistic effect to leading order in this paper. So let's now move to the second part of the talk. In the second part of the talk, I will use this gauge, this geodesic electron gauge. Yes, sure. This one is first order in Poisson gauge. This one is first order in Poisson. I don't show the second order because it will be like 4 slides, more or less. Because the advantage of GLC is that you have them right in a exact way. Then you have a coordinate transformation that go from this gauge to the Poisson gauge. So you have just to apply that coordinate transformation. In some way, you can obtain the second order expression without knowing the physics. It's just algebra. Instead, if you go do in the standard way, I mean, you go to Poisson gauge and you go to solve all your equation, like deviation equation and so on, then you have to be really careful because, okay, you can forget stuff. For example, I have to take in consideration post-Born contribution. I have to take in consideration the fact that your volume perturbation is perturbed also in transversal direction. So you can do it, but it's much more complicated. In this way, you have the exact expression, coordinate transformation, you get it. I mean, yes, so you solve one time to second order, and then to go to second order, all the cosmological observable that you want, you can use that coordinate transformation. It is a coordinate transformation, so it's quite easy to do it, to obtain it. Let's say to obtain to second order perturbation theory, the area distance in this method, you can take maybe, if you really like working hard, maybe 1 week. To do in the Poisson gauge, they say me that took 6 months. This is the scale of time. And then you can really check things because it's just algebra, so it's all there. It's Taylor expansion and algebra. You don't really, for example, in the other group, sometimes they forgot terms and then they put in other version of the paper. We have just everything from first shot. Just to say. So you have several advantages, let's say. Because you have things in exact way. So being exact, then it's everything inside. So you don't have to searching effect. You don't have to search effect. You can do like, you don't know anything about physics, your calculation, and then you go to look, this one is the lensing contribution. This one is the shift space distortion. This one is come from the fact that the velocity is perturbed in this direction, and so on. While in the standard approach, you have to think about this, otherwise you miss stuff. So let's see how this. So GLC gauge is really nice, perfect to measure stuff on our past light cone. But what happens if we don't have stuff on our past light cone? We have, for example, neutrinos. We can try to have some solution on, let's say, of the time of flight of neutrino from a source, cosmological source to ourselves. This will depend from their mass, from the energy, in general from the ratio between mass and energy. Let's say. So what it was in the lecture? It was like the time of flight of ultra-realistical particle, for example, neutrino, which received from a distant source. It will depend from the mass and the energy that measured by the observer. It will also depend from the detail of your space-time geometry between the source and yourself. If you have different geometry, you have different dynamic of your universe, so the neutrino will take different time to reach yourself. So what it was shown in some previous paper, let's say pioneeristic paper, it was that by Zatsepin, that the observation of this relative time can be used to have information on the mass of neutrino. And then it was pointed out by Stodowski that if we can measure the interval between the arrival of true neutrino emitted in the same moment from your source, then you could use this to have information about your cosmological parameter. However, this result by Zatsepin and Studowski were obtained in just considering homogeneous isotopic metrics, just Freeman-Robertson-Walker described this way. But the universe is not homogeneous. We have okay. Sorry. So what they get that this time of flight difference of two ultra-realistical particle, it was depending from the inverse Lorentz factor, using in the following way, where tau 0 it was the real time at observer of one of these particle. I mean, sorry. The source time it was at where there was the emission is written by tau s. M here the mass energy as measured of the observer. Z is the cosmological redshift. Just to describe this equation. But what we have is that the universe is full of structure at different scale. So the question is, do these inhomogeneities affect the time of flight of this relativistic particle? They change something. For example, at priori there was one could also even expect that this velocity, I mean this time of flight, it could depend also from different let's say term in different way for your Lorentz term from the ratio between the mass and the energy. And more generally, this inhomogeneity could affect, for example, the precision of your cosmological parameter extraction that you have from this kind of observable. So to answer to this question, we have used the geodesic coordinate, which is really good on the past icon, and it turns out to be enough good also to describe geodesics that are not null, but they are nearly null, namely geodesics where these ultra-relativistic particles they travel. So what we have in this case, I mean, the framework of this case is the following one. So we've described a family of almost null geodesics. We'll start from a source. They start together, the two ultra-relativistic particle. So they start from the source with lie at the past icon described by omega w equal to w0. So they both leave from this past icon, and then they depending on the value of the Lorentz factor, they will arrive to us on a different icon. For example, on an icon which is described by WWA. So in practice, we want to describe a geodesics with lie between two icons. We leave from this and arrive to us from this other icon. So you have a dynamics in this sense. So what we can do is just to take our metric, and from the metric to write the mass shell constraints in the following way. Where here a dot denotes the differentiation with respect to time, which is measured by the particle that is moving. Then if we rescale everything for the Lorentz factor at the observer, and we assume the following hierarchy between these different quantities that we have here, which hierarchy can be verified after we get our final result, we can write this equation, which is the question which hold at the leading order with respect to the Lorentz factor. We expect the inverse of the Lorentz factor. Namely, you have to assume that you have a part being this particle ultra-relativistic. You have to assume that if m is the mass of the particle, the energy of the particle is much larger of the mass, because you have to be ultra-relativistic. So this one is a really small quantity, and this is right at the leading order, and this is a small quantity. So then, in the same way, like just some algebra, it's not so important. The same way, you can write your geodesic equation, and then you can extract how I behavior w dot, and you can see that this go like gamma to minus 2. So this is consistent with the hierarchy that you make the hypothesis before. And then now what we have to evaluate this different time of flight is the derivative of w with respect to the proper time. I mean, you want to see how this icon change. And then you have the derivative is given by this. And then you can use the fact that time dependence of this quantity of JA, where JA is defined by this. The appreciably at higher order your ratio m over E. So we can you can take the value at the background at observer position given by this. You plug in again, and you see that the difference between WA and W0 is given by this expression, where to the leading order in the inverse Lorentz factor, we can take the arrival time of our coordinate just given by the arrival time of the first of the particle, let's say tau 0, because the difference will be give a contribution at next to leading order your final result. And you can do this average, you can do this integral, just doing the integral over the background geodesics. You don't need to consider the fact that your geodesics is perturbed, always at leading order in gamma to -1. If you want to go to higher order in gamma to -1, then these are all effects that come in, so the things are more complicated. So in practice, yes, in practice you have this time-like geodesics, and you want to see which is the difference between the arrival time. But this difference at leading order in gamma -1 is just given by this integral, where you have something that is perturbed, that are this quantity, that will depend from the fact that you have a perturbation theory from the mass and so on. But it's enough to project all this quantity on the light one. So if you want to go to second order in the inverse Lorentz factor, that will be more complicated. But to leading order, that it was, it was one of our new results, let's say. So what you have, if you take this, and you do this is just for one particle. So now you want to see the time of flight difference between these two different particles. You take this, two particles, you subtract each other, you get just this. And then you use the fact that at observer position, the proper time is just the difference between these two proper time is just given by this. You can see it's a consequence of the fact that on the observer position you make the hypothesis that you don't have inhomogeneities in practice. And then, as a consequence, you have that the difference between the arrival time of the first particle and the arrival time of the second particle, it will just given by this expression. So this is our main result. I show how to leading order in the inverse Lorentz factor. You have that the arrival time is really similar. It's very similar to the case of Freeman-Warshaw Walker expression. The only difference is that before, inside your interval, you have just the background redshift. Instead, now you have the perturbed redshift. This is the only difference. But in the same way, there is a factorization of the Lorentz factor that go outside your integral. Namely, the obtained geometrical correction are the same for the two particles, and they can be factorized out the integral, which helps a lot in using this kind of formula to do some physics, let's say. So now we have this expression, and we want to verify that this expression can still use also if we take in consideration the effect in homogeneities to do some cosmology. I mean, to measure the difference between the mass of the neutrino, for example, or to try to do some constraints on cosmological parameter. To do so, we have to see how the large-scale structural homogeneities affect your result. We know the power spectrum only through large-scale structure, so we do perturbation theory, and as a consequence, we want to write this expression in perturbation, expanded in perturbation theory, doing a similar stuff like did in the first part of the talk, namely writing our upsilon inversion as perturbed, and the time of that this particular measure also in perturbation theory, where all the time are given in this paper. We can finally write our difference between the time arrival between the two ultra-elliptical particle in this way, where the perturbation are given by this expression. But here, when I write, for example, eta, it means this. I mean, it means that I'm doing my integral on the background path like on my particle. And the V parallel is just the Mercurial velocity, radial Mercurial velocity, as we used also before. So you have your background value, like it's just the standard one, plus something that gives plus something that is perturbed your background value. So now, what I want to do now is to evaluate the variance of this background value. I mean, I want to evaluate the variance is the quantity that controls the dispersion of your data around the mean value. This can be defined in the following way. Is in general defined in the following way for whatever observable that you have. And then if I make the hypothesis that my fluctuations are stochastic, I mean the average out if I just consider one, if I do an average all over the universe. Then the variance is just stick to this value, namely is equal to the average of the square root of first order perturbation, the square of first order perturbation, average out, and then I do the square root to get the dispersion of the data. To evaluate this dispersion, we can go to Fourier space, for example. And to go to Fourier space, I will expand in Fourier space my gravitational potential in this way. And I make the hypothesis that they have a stochastic variable, namely that this can be derived in this way, where E key is just is a random variable that satisfies this ensemble average condition. And then, according to this, I can see, for example, that the average of the square of my gravitational potential is just given by the integral of your dimensionalized power spectrum. If I use this and I go back to my previous expression, try to do this expression, what can be noticed that the leading contribution to variance is just given by the redshift space distortion, because this one it will be the term that you have the higher factor of k in Fourier space. So having the higher factor of k in Fourier space is the one that will give the largest contribution from the, let's say, the ultraviolet tail. If I write then if I write this contribution in Fourier space, we will get the following result. Namely, we'll get the power spectrum with a kernel that go like k to the third. So it's convergent, but is just say something that it can give a non-negligible contribution. And in doing this integral, I assume like as infrared cutoff, I assume just the horizon scale nowadays, like because we cannot know what there is outside the horizon scale, of course. And at least if we don't assume a model, and as ultraviolet cutoff in the numerics that I will show in a minute, I assume the largest scale below which we can use we can give a linear description, we can describe our let's say our scale large scale structure using linear perturbation theory. Sorry, and because I mean, if I consider nonlinear effect, I have to go. Perturbation theory is not valid anymore. So in this way, I can only describe the impact on the dispersion of the data given by large-scale structural inhomogeneities. So then, to better quantify the possible impact of this scattering on my data, I want to see which is the impact of this scattered if I look to the present, let's say, constraints that we have on our omega lambda. Namely, I want to see the dispersion sigma 8, which is caused by the present experimental uncertainties omega lambda. So let's assume to this value from the particle data group paper, and I define this dispersion as given by the time of flight difference background level when I assume the minimum value of omega minus the one when we assume the largest value of omega over 2 times the one of the future model. Then let me show the numerical result. It's probably the most interesting part. So what you can see here is the expected fractional dispersion, so I mean the dispersion that we looked before, that we will measure when we measure this flight of time difference of two ultra-relativistical particle, or for example, of one relativistical particle, a photon or gravitational wave. For CDM, this curve, lambda CDM, this curve, is the one instead that is related to the fact to the uncertainties about what we know about the omega lambda, for example. Well, we could choose other parameter. In this case, we choose omega lambda, that is the more important one. So as ultraviolet cutoff, we choose the linear scale given by this. So you can see from this figure, if, for example, you take in consideration lambda CDM, you can see that you could, in principle, measure omega lambda using the time of flight difference between two ultra-relativistical particles, if, of course, you will know from other experiments the mass of the neutrino and energy of this particle from, for example, your modeling or your source. If, for example, if you have a source that is at redshift larger of around 0.35, because in this case, the variance that you get from the time of flight difference is less of the variance that you get from presence constrained omega lambda. So if with just one source, if you know the mass of the neutrino and your energy, you can measure omega lambda at much higher precision of what does Planck now. I will cite the paper. We'll give some number in the end of the talk. But let's. No, that's the point. I mean, that's the point. I mean, this doesn't depend on the mass of the neutrino on the energy. Does not, because you are looking to the dispersion. So this because you factorize out the Lorentz factor. So this doesn't depend on the Lorentz factor. But of course, you have. It does not. So I decided that. Sorry, it does not. So of course, then the real possibility to measure this kind of thing, it does, because you have to have a large mass. You have to have, for example, nowadays with the detector that you have now, you cannot measure this. This is the dispersion, so you have no, it's adimensional, so you have no units. It's percent, say. So let's say, so this is over 1. So let's say, for example, 0.01 is 1%. So what you were saying now. So you have that both sigma and sigma height are independent from the ratio of for the Lorentz factor, because these they factor out. So in practice, your dispersion is independent from the energy and the mass of neutrino. It will be is a general result. On the other hand, if you don't care about cosmological parameter, you say I take cosmological parameter by Planck, and I look to this tail. Instead to look to this tail, I look to this tail. So in this case, the impact on sigma, your cosmological parameter, is much less of the impact instead given by the variation of your mass and the other quantity, the other contribution that you have in the other quantity that go in this dispersion. So I want to look. I want to look on the Lorentz factor. I want to try to measure the Lorentz factor with my detection. Then the theoretical error sigma will impact this, and the relation between the dispersion the error that you have or your Lorentz factor with your measure will be the half of the dispersion. You can see this because because here you have a square. So the error that you will have using this to evaluate the ratio between the mass and the energy, it will be 1/2 of the error that you have on the time because you have a square. Just so let me as to conclude, let me show this figure, but for the range between 0.01 and 0.1, that is the range, the typical range in which you could maybe have a detection in the future from a supernova, from gravitational wave event. And then you can see from this figure that if you have a detection in this range, then the error that you will have from this detection on the measure of the Lorentz factor or the massing as you know the energy is always below, let's say, 5%, because there is a factor 2, so it will be always below 5%. That is not bad. I mean, we don't have a measure at all at this moment. So let me conclude and summarize what I say. We have in the framework of Geodesic like coordinate, we can evaluate the time of flight difference of ultra-radius particle in exact ways, but at the leading order in the Lorentz factor. Then we see that we have shown that realistic inhomogeneities, let's say the one that come from large-scale structural inhomogeneities, they seems don't impair the possibility to extract information both from particle physics and cosmological side on this kind of measure if one day will be available. And we have seen, for example, we have to determine the value of omega lambda with a better accuracy with respect to one does with CMB example. It will be enough to have one source at a redshift larger of 0.36. It's not a small redshift, but I mean, let's hope for the future. And we have to see that the error induced by these homogeneities on the determination of the Lorentz factor via time of flight difference, it doesn't exceed the value of 5%. But let me conclude, trying to be honest, that the main obstacle to this kind of physics lie on the fact that it's really difficult to find the appropriate source with the time of flight observation that are both possible, is sufficiently free from other systematic error, and where we can really have a good model of the source and see when the true neutrino they really are emitting the same moment, or which is the different time of emission and the source, and so on. And to have some number, for example, like I would say really optimistic one, you can look to this paper they make some, hypotheses, and they say that maybe in the future that we will be able to use this kind of physics to detect neutrino, if we detect neutrino in another way, to constrain cosmological parameter.